Alrighty, good afternoon or good morning, or I have no idea what time it is when you're actually watching this. Today we're going to talk about the metric system because we're entering Unit 2 on measurement and maths. So why is the metric system relevant? Well, scientists have to communicate things with one another, and we needed a system of units to report data that was universal. So you probably know by now, but we use inches and feet in the US, but everywhere else in the planet uses centimeters and meters because that is a universal system. So we're the odd one out, which makes it hard to communicate universal data with people from other countries often. But in science, even in the US, we use the metric system. So this is actually referred to as SI units, and that comes from the French. I will let someone else, like David, pronounce that, but I believe it's something like Système International d'Unités. No, that's probably bad. But it's an international system of units. So it is a French origin, obviously, and it is the modern form of the metric system. So the original metric system was formed a while back, but the SI unit system that we use today internationally is just a sort of more codified form of that. France, see? Look at that. Okay, so the big thing are our base units. So these are defined units within a system of measurement. And the reason these are different from all the other units we use is that we actually say, okay, this right here, I'm going to say this distance is a centimeter. We just all have to agree that this is a centimeter or whatever it happens to be. And there are a few base units that we use to derive all of the other units. So these are independent of other things. So the 7 base units in the metric system that we need to talk about are these guys. So time, length, mass, temperature, amount of a substance, and then electrical current and luminous intensity, but we're not going to use those last two in this course. So for time, the base unit is second. For length, the base unit is a meter. For mass, the base unit is a kilogram, and this one's kind of weird because it has a prefix. We'll talk more about prefixes in a second, but that's a little weird that it has a prefix. And then temperature is Kelvin, not Fahrenheit. Do not say the F word in this room. And not even Celsius, although we will use Celsius a lot. Amount of a substance, we use the unit mole. And then for current and luminous intensity, ampere and candela. And on the right, you have the symbols, the little abbreviations for all of those. So go ahead and take a second, pause the video, and write those down in your notes. All right, so those are the base units. And again, like I said, we derive other units that we call derived units from those base 7. So we actually combine different units of our base and we create other ways to measure things. So can you think of any common derived units? Pause the video and think about this for a second. So I'm going to start with speed, right? Distance over time. You might think like, oh, a speed is just like, there should be a speed unit. But if you look at what makes it up, right, it's got meters, so this measurement of distance, divided by seconds, divided by this unit of time. So both length and time have a base unit of our original independent units, meters and seconds. But we combine the two in this method here, and we get a new derived unit. The next one we're going to talk about is volume. So for solids, we typically measure volume in cubic length, such as meters cubed or centimeters cubed. And for liquids, we use liters or milliliters. So those are the two symbols for meters cubed and liters. If I have a little cube that's 1 decimeter on all of its sides, then that is equal to 1 liter of liquid, whatever it is. All right, and the last one is density, and we've already talked about this, but it is a mass divided by a volume. So you actually have 2 derived units, right? One is volume itself, the grams per centimeter cubed or the grams per milliliter, but the other derived unit is the volume part on the bottom, right? The centimeters cubed or the milliliters, those are both derived units. So take a second and jot these down in your notes, pausing the video if you need to. Whoa, that's a lot of stuff. So temperature, a little bit different. This measures the average kinetic energy of particles in a substance, right? So Kinetic energy is just the energy things have in motion. And this is measuring the average kinetic energy of a certain sample. The SI unit, as mentioned before, is Kelvin, so capital K. And this is the same size as a Celsius degree, which is kind of weird. So Celsius and Kelvin, they have the same magnitude. Like from 0 to 1 Celsius is 273 to 274 Kelvin. But what you might notice is different there is where Kelvin starts versus where Celsius starts. So the temperature in Kelvin is equal to your Celsius temperature plus 273. And then same thing, but reversed, your Celsius temperature is your Kelvin temperature minus 273. And that's Lord Kelvin. What a guy. So for water, its boiling point is 100 degrees Celsius, and its melting point is 0 degrees Celsius. So if I were to try to find the boiling and melting point in Kelvin, I'm just going to apply this, right? So this equation right here says take your Celsius and add 273. So 100 plus 273 tells me that water's boiling point in Kelvin is 373 Kelvin. And then its melting point, again, just add 273 to 0. Well, you're going to get 273 Kelvin. And notice we don't put degrees Kelvin, it's just Kelvin. When Kelvin is equal to 0, we are at absolute 0, and this is the point at which all atoms stop moving. This is not something, as far as I know, we've actually been able to fully recreate in a lab setting, but it is, in theory, possible. To round out today, we are going to add all of these SI unit prefixes. Some of these should be familiar to you, right? Like you've got centi, milli, probably seen kilo a lot. But some of these you might not be familiar with. So I'm going to roll through them one by one. And it's very important that you write the symbol as well as the value. So the symbol tells us how to write that unit as a little shorthand, but the value tells us how big is this prefix communicating something to me, to be. So first off, we have a gigameter, gigagram, gigasecond, whatever. And this is equal to 1 billion of your base unit. So for all of these examples, I'm going to give a little sort of conversion. So 1 gigameter, right? 1 gigameter is going to be equal to 1 times 10 to the 9th power meters. And we'll talk more about scientific notation later, but 1 times 10 to the 9th means 1, 3, 4, 5, 6, 7, 8, 9 zeros. So you can see here, got 1 billion meters. That's 9 zeros after the 1. All right, a mega is equal to a million, so it's 6 extra zeros after 1. 1 megameter is really big, and then if you have a bunch of those smaller meters, you can get up there. Kilo is a lowercase k, not a capital like giga and mega, and it's 1,000 or 1 times 10 to the 3rd. Hecto is 100 regular meters, and a decameter, it's got kind of a funny prefix, dk, is equal to 10 of your regular meters. And it's important to note, I'm using meters for all of these, but it could be seconds, it could be grams, right? I could say 1 hectometer equals 100, or sorry, 1 hectogram equals 100 regular grams, or 1 decasecond equals 1 times 10 to the 1st regular seconds. And then we have our base units. So your base units can be any of those primary units, not just the base unit. So, all right, now from here on, as we go below base unit, we're going to be looking at units that are smaller than your original base unit. So a decimeter, little d m, is 0.1 of a regular meter. So this is 1 times 10 to the negative 1st meters. So in my example above, right, I moved the 0 to the right 9 places to get this many. But if I take, let's see, 0.1 decimeters, right, it's the same thing as taking 1 and moving that decimal -1 places. So what does that mean? Well, that means I take a regular meter, 1.0 meters, and then move that decimal place 1 place to the left. So 0.1, and then this would be decimeters now. All right, centi, it's going to be 0.01, so you're moving the decimal 2 places to the left. We've got milli after that. It's moving the decimal 3 places to the left. And then our jumps become much bigger. So we got a micrometer. And these use a very funny unit. It is a U with a little tail on the front. So this is actually the Greek letter mu. So a micrometer is a millionth, or -6 places, right? So you move that 0 6 places, or you move the decimal 6 places to the left. We've got a nanometer, which is a billionth, and then we've got a picometer, which is a trillionth. So 10 to the -12, 10 to the -9 on both of those. So take a second, pause the video, and jot all of these down. All right, so mnemonic devices for all of these prefixes. It is very important that you find some way of memorizing these. You do not have to use these. I'll be honest, this one right here I kind of hate, so I wouldn't do that one because it's stupid and body shaming. But I do like this one down here. Great mighty King Harambe died, but don't cry, my memes never perish. It's pretty quality stuff. But what you really need to know about the prefixes, you need to know the symbols, so capital G, then capital M, then lowercase k. But you also have to know the powers between these things. So what do all these dots mean? Well, it means to go from giga to mega, it is 1, 2, 3 times that you're moving that decimal place. So what does that mean? Well, if I had 100 gigameters, I would have to move its decimal place 1, 2, 3 places to the right to get to a mega. So 100 gigameters is equal to 100, move that decimal 1, 2, 3, and then fill in my spots. That's equal to 100,000 megameters. Make sense? And then in the same way, all of these dots that aren't there, right, between kilo and hecto, there's no dot. So it's just one jump. Between hecto and deca, just one jump. You can make up your own mnemonic device, or you can just use King Harambe, or you can just try to memorize it brute force. It's kind of up to you, but make sure you write these down, and then we'll do a little practice with conversions. Okay, so this question right here, we're going from gigaliters to regular liters. So regular liters means our base unit. So how many places do I move my decimal to the right? Well, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go 9 places to the right. So if I move this decimal where it is, 1, 2, 3, 4, 5. So now the decimal is after the 5, and then I need to make 9 places total. So 6, 7, 8, 9. So if I look at the little gaps I've made, I'm going to need 1, 2, 3, 4 zeros after the 5. So I've got my 5, and then 1, 2, 3, 4 zeros. So that is 50,000 liters. All right, milligrams, we have 720,000. We're going to go to decagrams. All right, so milli, we're starting right here, and we're going to decagrams. All right, so I'm going back to the left. So I'm going to move the decimal 1, 2, 3, and 4 places to the left. So look where my decimal is now. And I'm moving it 1, 2, 3, 4. So that decimal is going to be right behind the 2. So I've got 72 decagrams. Easy. All right, this next one, centimeters to meters. So centimeters right here. Meters is a base unit, so it's going back to the middle. I just need to move it 1, 2 places to the left. So right here, my decimal is on the right. It's an invisible decimal. 1, 2 places to the left. So this will be 5340, and then that decimal. All right, so we've got megaseconds right here, and we're going to regular seconds, our base unit. So I've got 1, 2, 3 jumps to kiloseconds, and then 4, 5, 6 jumps to get to my base plane second. So if I move this decimal here, 1, 2, 3, 4, 5, 6 places, I should get 0.27 seconds. Cool. And then last one, pico to nano. So pico's all the way over here. Nano's just to the left of it. So it's 1, 2, 3 jumps to the left. So I'll take my decimal in picoseconds and go 1, 2, 3 to the left. So I've got 89.124 nanoseconds. That's about it. We're going to do more of this practice in class on our next class period, but metric conversion is something you will get the hang of very quickly. Thanks, y'all. Make sure you've jotted this down.